Lesson 8. Weight, mass and gravity. Hopefully this should all be familiar to you. We've introduced this in Year 7 in the Spaces module. We've done it in Year 8 in the Forces module. We do it again in Year 9 in the Energy and Forces module with me. And now we're doing it in Year 11, which is this topic. So, ever since you've been born, you've lived inside a gravitational field. It's the most natural thing in the world to know that you are pulled to the ground. You can jump and get yourself off the ground, boop, boop, but you ain't going to get far. Because you have the entire gravitational field of a whole planet pulling you down. And it's pulling you towards the centre of its mass, like so. So it doesn't matter where you live on this planet, this nice little sphere, you are pulled towards the centre. So when we all point to down, what we're actually doing is we're pointing to the middle of this big ball of rock we all live on. So, what's causing weight, mass and gravity? Well, the first one is stuff. You are made of stuff. Stuff's a great word because you can have atom stuff. The atoms can get together and form things called molecules. So, molecules. You then form cells. It all means the same thing, stuff. So you are made of matter. So matter exists and we measure it and we call it mass. The mass of an object means how much matter there is. So when you look at something, you say that is massive, it means, jolly gosh, there's a lot of stuff there. You're looking at Chungus, the largest elephant in the world, and you say, well, that's a massive elephant. You mean there's a lot of mass of the elephant. So that's the first one. Next, not entirely sure why this is, but every little particle in the universe gives off an invisible field called gravity. It is a force that is emitted. It's emitted by you, and it's emitted by the planet, and the planet pulls on your mass. Now, if you could see gravity, it would be like light coming off a light bulb. It gets fainter the further away you get. But we live right on the surface, so we get the full effect. So, gravity emits off the planet and pulls upon you down on the planet. So, gravity. Gravity. It is a non-contact force that pulls on mass. Okay, so it acts on matter. Non-contact because you could be up in the air on an aeroplane, it's still pulling down on you, so you don't have to have contact between you and it. That's different to other forces like contact forces, for example, friction, air resistance, pushes and pulls where you're touching the object. Those are contact forces. So, matter is mass, stuff. Gravity, a non-contact force. Last piece of the puzzle. The gravity reaches up, grabs every atom of you, pulls it towards it, and it creates a force downwards against the ground where your feet are hitting, and we call that force weight. So technically you only have weight while you are in contact with something. If you are up in space and you are orbiting the Earth, you are weightless because you're not in any contact with anything. You're not pushing against the surface. We'll talk a little bit more about that in a minute, because everybody thinks there's no gravity up in space, and there's loads. So, units. Again, easy to remember, sometimes confusing people. Gravity will tell you how many newtons per kilogram you'll get. Let me thicken that up a bit. How many newtons per kilogram? So if you have 1 kilogram on the Earth, 1 kg, gravity of the Earth is 9.8. You will get 1 kilogram will equal 9.8 newtons of force. There is another unit for it though. Gravity makes things fall. And in lesson 2, when we did about acceleration, we saw in the equation v squared minus u squared equals 2as that if you were dropping things, then gravity is the acceleration. So you can also write it as meters per second squared. Mass is kilograms. Weight is a force, so it's in newtons. So let's have a little look. What would happen? Let's go over to gravity a minute. Weightlessness. I love the idea. Blew my mind when I was a kid when I learned this. We live on a planet. Let's just draw the Earth for a second. For you and me, we can see about 20 miles before the curvature of the Earth kicks in and you can't see any further. Now, if you throw something, it goes over and then it falls. Throw it faster and harder, it'll go a bit further, it'll still fall. The beauty of Newton was he said, well, what if you could throw something from high enough and far enough, so you built yourself a little tower, and you stood on the top of the tower, and you threw something, and the curvature of the Earth matches the curve of the object trying to fall. So maybe you don't throw it enough and it hits the ground there, but you decide to build something faster, I don't know, for example, a rocket. Hopefully you all saw SpaceX launch on Saturday night, and you launch it so that it goes into orbit. And so that's how things stay in orbit. They're falling, but missing. And what about the people up in the International Space Station floating along? You look at the videos, they're floating. They have no gravity, but they do. Gravity is coming off. It goes right out, pulls the moon towards us. Of course, there's gravity. But each of those people is likewise falling at the same rate as the ship. The ship is trying to fall, so it's going round. The person is going round trying to fall, but they're constantly missing. So it gives the impression that there is no gravity. So actually, officially, they call it microgravity. But there is most definitely gravity. You're just falling, but missing. Right. Next, let's have a look at other planets. So let's take... I haven't done the equation. I need to do the equation first. Let's have a quick look. Hopefully most of you will know it by now anyway. We'll get rid of this rocket. That was my previous attempt at teaching when the voice didn't record. The equation, really easy. Weight is equal to mass times gravity. W equals mg. And if you're so inclined, draw a little triangle. Go on. There we go. Put it in a triangle, nice and easy. Weight, mass, gravity. Cover up the mass. Cover up mass, get weight over gravity. Cover up gravity, get weight over mass. So it rearranges really easy. Let's have a little look at our experiment here. What would you weigh if you only knew your mass? So you get on some scales. We've all put on a bit of corona weightage here. I think I've put on about stone. You get on the scales, you have a little cry, and you promise yourself you're going to get fit, and then you don't. You go and eat a Mars bar. Or is that just me? So you got your mass, 50 kilograms. You want to find out what is your weight. So you look it up. Earth, 9.8. I'm going to round it off to 10 because I can't do 9.8. Or can I? Yes, I can. 10 times 50 is 500 newtons. 0.1 of that number is 5. 0.1 equals 5 newtons. I'm just going to take 10 off that. So I get 490 newtons. Yeah, ignore that. I have 490 newtons of weight. So that's that. What if I went to a different planet, though? What if I went to Mars, which hopefully in the next, I would say, 7 years, conservatively, I think you're going to see a human being on Mars. They're going to weigh less. Mars is smaller, emits less gravity. The gravity is about a third of what we have, so you would weigh a third of your weight on Mars. So would you have less mass? Would you have a third of the mass? Hopefully you're saying no. To lose mass, you'd literally have to chop a bit of your body off and have less atoms. And that's not going to happen anytime soon. So what I would like you to do to finish off this, copy these down, press pause right now, do a little table like this, press pause right now, write down in the gravity for each one, and then calculate your weight. Now you can go up and use your scales, but if that's too depressing for you, just use 50 kilograms. Have a little go, and any problems, put them in the comments, take a picture, put it up and press hand in, makes me happy, and see you later. Bye bye.